Welcome, everybody. Thanks for joining us. My name is John Ferguson, and I am going to be talking to you today about signal processing and deep learning with the Deepwave digital products and with GPUs. So I want to start this webinar by discussing what Deepwave Digital does. So we work on hardware and software products that help enable our customers to incorporate deep learning and signal processing into wireless systems. These can be for signal identification, interference mitigation, electronic protection, or many other applications. Basically, we want to live at the center of the diagram on the right-hand side of your screen. So if it involves deep learning, signal processing, and wireless, then that's the sweet spot for where Deepwave Digital operates. Our customers range anywhere from wireless OEMs to operators, defense contractors, government agencies, and of course, university researchers. We are located in Philadelphia, Pennsylvania, and founded in 2017. So let's talk about some of the major challenges that are facing RF or radio frequency systems. One big one is congested spectrum. As everybody wants more and more bandwidth, as 5G comes online and there's tons of IoT devices and high-speed systems out there, the wireless spectrum is becoming more and more congested. And spectrum is not something that we can just create, so we have to go about using it more efficiently. And Deepwave Digital feels that utilizing and leveraging machine learning methods is the key to solving the congested spectrum problem. Then there's things like interference. As more and more devices become active on a network, the amount of cross interference between channels and interference between different devices becomes more prevalent. And then, of course, electronic attack or jamming. If you're in the defense world, then this is a major concern. And we feel that there's a lot to be done in terms of machine learning to try and help mitigate electronic attack. And of course, everybody is concerned with cybersecurity, and there's been a lot of work out there that have kind of shown how machine learning can help with that. But we don't want to come across as saying that machine learning is going to solve all of the problems in RF systems. In fact, we don't think it is. We believe that machine learning really thrives when it is at the intersection of where you have a complex problem and there's also no analytical solution. So what I'm going to do is I'm going to kind of walk through a rudimentary wireless stack here. So what we have looking at the bottom left-hand side is we have a user application. Now this could be something as simple as an application on your mobile phone. So what happens is, let's say you have the Amazon app open and you want to take a photograph of a pair of sneakers, and you want those sneakers to, you basically want to know what those sneakers are. So what you would do is you take a photograph of it. That photograph would be turned into a series of ones and zeros. We would send that up. We would modulate that data, turn it into a waveform, and then we would take that modulated waveform, frequency convert it and transmit it across the air. The tower would then receive that signal. It would then down convert it in frequency, demodulate it, turn it back into a series of ones and zeros, and then it would analyze the image and tell you, and then do the reverse, send it back to you and say, this is the set of sneakers. Okay, so that's a very rudimentary view of how a wireless system operates. And I'm just going to walk up this stack and say, where could we apply machine learning? So the majority of applications so far have really been at the application level for machine learning. Now you could say taking that photograph of a sneaker and then using machine learning to tell you what type of sneaker it was, that was in fact using machine learning. But that was using it on the data content. So this is really where the majority of work has been done to date. The next layer up is the modulation layer. So this is where you're starting to get into applying machine learning to the wireless technology itself. So we can do anything from advanced modulation techniques, adaptive waveforms, look at encryption and security. And then there's another layer up here, the spectrum and network-centric application layer. So here you're doing things like signal identification, monitoring for threats to your spectrum, dynamic spectrum allocation or intelligent spectrum usage. We talked about electronic protection earlier. All of these things, this is really where they live. So let's talk a little bit about signal identification. And I always like to start this slide with a photograph of a cat. So the thought experiment we're going to walk through is we want to create we're going to write down an algorithm that is able to classify photos of cats. So you look at this and you say, okay, so I'm gonna write down a system of equations. I'm gonna make my algorithm look for 2 pointy ears, 2 eyeballs, 1 nose, maybe it's gray, and then we'll write all of that down and try and classify a cat. And then we run into a problem where this is also a cat, but we also have to classify this. So it no longer has pointy ears, so now we have to take that into account. And then what happens when we have something that's even a little bit more crazy like this cat? So we then have to further modify this algorithm, and you can see where this is going. It gets more difficult and more difficult and becomes a larger and larger problem and becomes ultimately intractable by writing down a system of equations. And then we even have another problem, is that is not even a cat right there. That is a lynx. So now we have to determine the difference between a lynx and a cat. And that's also not a cat, that's a leopard. So that's really a difficult problem to solve. And that is where deep learning excels. So deep learning identifies these intricate patterns that are too obscure and subtle to be implemented in a human engineered algorithm. So this is really the sweet spot for deep learning. And so what we're talking about doing is taking the same type of methodology and applying it to the congested wireless spectrum here. Okay, so in today's talk, I'm going to walk through this basic outline. So we'll start off, I'll go over our AirT product. That stands for Artificial Intelligence Radio Transceiver. And then we'll go through the software stack associated with that, which is AirStack. And then I'll get into some demonstrations. The first set of demonstrations will be live operation on the AirT doing signal processing. And in that section, we'll go through cuSignal, some recent work that we did with NVIDIA there. And then we'll go even further into touch on some deep learning workflow. Okay, so this is Deepwave's main product, which is the Artificial Intelligence Radio Transceiver, AirT. It is shown in the photograph there, and it basically consists of analog devices, 9371 RF front end, an FPGA, and an embedded NVIDIA Tegra TX2. So that's the hardware side of it. It is an edge compute platform. You deploy it in the tower, in the drone, or even just doing research in your laboratory. The software stack that runs on it is what we call AirStack. So looking at the bottom of the software stack, we have our AirT hardware. And the next layer up is the operating system. That operating system is based on the NVIDIA Jetpack. And then we have the AirStack firmware. That is the firmware that is on our FPGA. The next layer up are our AirStack drivers. We provide these for you with the product. And then the next layer up is the deep learning and signal processing libraries. So Deepwave Digital is not trying to create our own deep learning library or our own signal processing library. What we are doing is we are supporting the industry standards there. So not trying to compete with TensorFlow. We support TensorFlow, we support PyTorch, any of the above. And then the next layer up are our AirStack Python bindings. Some of these are third party, some of them Deepwave contributes to, some of them that we provide ourselves. And this ranges from CPU signal processing, GPU signal processing, and of course neural network inference. So the AirT is a software-defined radio that is ideal for neural network inference. So looking at a little bit more detail of the AirT, it is a mini ITX form factor. The PCB rendering is shown there on the left. It consists of an analog devices, 9371 RF front end. that is tunable from 300 megahertz to 6 gigahertz and 100 megahertz of bandwidth. The data is then sent to the Xilinx FPGA, which is also over here. There is a timing and clock circuit that ensures everything is synchronized, and then the data is DMA'd over to the NVIDIA Jetson. Now, the NVIDIA Jetson contains dual CPUs, so it has a ARM A57 quad core, and then it has a Denver 2 core CPU on there. So both of these are embedded CPUs, and then it also has an embedded Pascal 256 core GPU. And the nice thing about these embedded GPUs is that they have a shared memory architecture. So the CPUs and the GPUs share the same memory. So the memory copy that is typically associated with PCI Express based GPUs is not present here. So we're able to eliminate one of the copies. And then we have a lot of I/O here. So because it's got the NVIDIA Jetson on there, it actually runs full Ubuntu. So you do not need a laptop sitting next to this. You do not need a computer sitting next to it. It is the computer. So you plug in your keyboard, your mouse, and your monitor, and you are off and running. And I will demo that in a few minutes. So let's talk a little bit about that shared memory. So on the left-hand side here, I have a traditional software-defined radio setup if you wanted to use a GPU. So what you have is the transceiver over here DMAs into system memory. So you transfer the data, the signal data over to system memory, and that is associated with the CPU. So you could do, this is kind of where signal processing on a software-defined radio has been in the past. So if you had a laptop and you were just running, doing your processing on the CPU, this is kind of all you would have. If you added a GPU to the PCI Express bus, then you would be able to do GPU processing, but you are going to add some extra latency associated with the copying from the CPU memory to the GPU memory. On the AirT, specifically because it uses the NVIDIA Tegra module, we have that shared memory, so you do not have that extra data copy. And depending on your application, that extra data copy could add up to 50 milliseconds of extra latency. So this shared memory architecture is really what makes the GPU capable of real-time signal processing. In our opinion, it is really kind of a game changer compared to the traditional PCI Express data transfer. So the AirT comes in two models, and they are basically the same except for the FPGA. So the traditional, the original AirT is the 7101 that has 2 transmit, 2 receive channels. It's tunable from 300 meg to 6 gigahertz. And it either has manual gain control or auto gain control. 256 GPU cores, 6 CPU cores, it's a dual processor, and then that 8 gigabytes of memory. The difference, like I said, between the 7101 and the 7201 is the Xilinx Arctic 7 FPGA. So there's a significant bump up in logic cells, DSP slices, and memory when you go to the 7201. Okay, so now let's talk about our software stack. So just bringing back this, this slide to remind everybody of the software stack layer. So the first thing I'm going to dive into is how you train, a really high level overview of how to train a neural network, optimize it, and deploy it on the AirT. And so that's shown in this flow chart here. So looking over here on the right-hand side, the first thing you do is you obtain your data, and now you want to train it. So we're gonna train a neural network to do something like signal classification. So we have a data set, we run it through our favorite machine learning training software. So that could be TensorFlow, PyTorch, Caffe, MATLAB, Keras, any of these. They are all supported by the AirT. So you train your neural network, and then you save that output file. Then you take your trained neural network and you optimize it using NVIDIA's TensorRT. So TensorRT is NVIDIA's neural network optimization tool that prepares a trained neural network for inference. So what it's going to do is it's going to go through your neural network. It's going to figure out layers that it can fuse together. It's going to figure out layers that can be put into the same CUDA kernel. It's going to get all that stuff put together. It's even going to go through and look at the precision with which you're doing computations and optimize all of that. And the output of TensorRT's optimization routine is what we call a plan file. And that plan file is what is supported on the AirT. And because we support that plan file, we therefore inherit all of the toolboxes that are supported by TensorRT. So you then take that plan file, you then deploy it on the AirT. We have a few different ways you can do that, either using GNU Radio or communicating directly with the Python drivers. Okay, so that's a high-level overview of deploying a machine learning algorithm, or the workflow for machine learning to deployment on the AirT. Let's talk about the signal processing side of things. Or better yet, let's talk a little bit more about the Python bindings. So if we zoom into these Python bindings, I'm going to kind of walk through the different APIs that we support. So if you want to do CPU signal processing, that's what I'm showing here. So above the dotted line are the Python bindings, and below the dotted line just kind of shows the hardware that you can execute this on. So lots of people are familiar with GNU Radio. GNU Radio is fully supported by the AirT. It runs natively on it. Many people use NumPy and SciPy to do signal processing, and both of those are supported on the ARM processor. So that's the CPU on the AirT. The next column is GPU signal processing. So because it has that NVIDIA GPU, we support CUDA. And with that, we get all of these nice CUDA libraries or bindings. So the most intricate thing you could do, the fastest and best thing you could do if you would like to, is to create your own custom CUDA kernel. That's where you're going to get the most horsepower out of the product itself. But if you do that, you're writing in C or C++, and you are likely, you're going to have to do a lot of hand tuning and optimization there. But if you have an application that you need to squeak every last ounce of compute out of the AirT, that is how you would want to go. There's also a lot of other bindings, Python bindings for PyCUDA, Numba, looking at CUPY. So CUPY is a great library that basically mimics NumPy, but has everything all the computations performed on the GPU. And then I will also be talking about cuSignal today. So cuSignal is has the same function calls as scipy.signal, but it's GPU accelerated. And we've been working with the Rapids team at NVIDIA to make that run well for real-time signal processing. Lastly, we have neural network inference. So there's really two main options for there. So you're going to want to use the GPU for this. I guess you could use the FPGA if you would like to as well, but the system was really designed for neural network inference on the GPU because that is very quick and you can rapidly deploy it out there. So we support TensorRT. You can also just communicate directly with those bindings, or we have a GNU Radio open source library called GR Wave Learner, which allows you to insert a trained neural network into your GNU Radio flow graph. So in the presentation today, the dotted red lines here are the ones that I'm going to be covering. The rest of them are going to be dedicated to a future webinar. And in particular, what I'm going to go over right now is the AirStack drivers. Okay, so here is the demonstration setup for my AirT that I have next to me. Looking at the left-hand side, what we have is the front-facing SMA connections and the power button here. I have an antenna connected to RX1. And then looking at the back of it, all we have plugged in is Ethernet. That's so that I can provide you the display here in a second. There's an HDMI display, which is actually providing the display to the local monitor. I have a wireless keyboard plugged into the USB port, and then of course power here. Okay, so the first demo that I'm going to show is a nice signal display, spectrum display that is open source. It's SDR Angel, and I will go through that now. So what we have here is a no machine instance being run on the ART next to me so I can get the screen capture all in one place. So this is actually running locally. So I'm going to maximize this, and I am going to select the LTE settings here. This just tunes to an LTE band, and I'm going to hit play. It's going to take it a second to turn on because the AirT has some, let's see here. The AirT has some calibration routines that are run in the beginning. And so that's for LO suppression, for quadrature error correction, and things like that. So you can see, it's a very nice display. Again, this is open source. You can see it on GitHub. There's our LTE band. We can retune this just by dragging the mouse. If it looks a little bit choppy, I apologize. It's because we are on video here, recording a webinar. So yeah. So let's try a different one. We can switch over to the CBRS. And so what CBRS is it's the 3.6 gigahertz band. And in this band, it's occupied by Navy radar. It's received a lot of press lately because we are going to be repurposing it when it's not being used for Navy radar, for LTE and 5G networks. But as you can see, there are some radars out there. You can see the pulses going, the spinning radars going on and off as they illuminate my direction. So you can see there's a bunch of them there. Okay, so this is just supposed to be a real quick demo demonstrating something really easy to do for spectrum display on the AirT. Okay, so I will stop this. All right. Okay, so back to the presentation. Okay, so that is the first demo that I'm going to show, and all of that is the AirT is capable of that. So now let's walk through our actual programming interface. So this is kind of the basic level source code for how you would interact with the AirT. Let's kind of walk through this and code snippets. So the first snippet is we're importing our packages. So the AirT leverages the open source SoapySDR framework. Now that framework allows for third parties to write plugins, and we have written an AirT plugin for SoapySDR. It is a great library. If you've never used it, I highly recommend checking it out. The next block code defines the RF parameter. So here we're defining which channel we want to receive on. So this is channel 0, how many samples per transfer, the sample rate, 125, so that's our full sample rate, the tune frequency, if we want to use AGC, all that stuff. Then we need to initialize the radio. So we kind of walk through here and then set our settings up. We have to then create a buffer to read the data to. So as the data comes off of the radio, where does it go? It goes into this buffer. And this buffer becomes very important when we start talking about GPU processing, because we want to allocate that in a way that's GPU friendly. Next, we turn on the radio. So at this point, we are starting to stream samples. And then we create an infinite loop where we are trying to read samples. And then if the user control sees, we leave the loop. And this is exactly where you would insert your code. So right now, all this is doing is just reading samples and then doing nothing and reading more samples, so overriding the buffer. So you would insert your application here, and then if you wanted some cleanup code, you would insert that here. And then finally, the last thing we do is deactivate the radio and close the stream. Okay, so now I'm going to show you the next demonstration, which is basically just that code right there. So we'll go back over here to our radio, and I conveniently have a different desktop set up with this code here. So this is the exact same code that I showed you a second ago, and we are just going to execute this. So this is all available on our GitHub page on the webinars section. So you'll be able to download all of this source code. If it's not already there, it will be there very soon. Okay, so I'm in the webinars directory here, and I can see all of the codes that are there. So I am going to call Python, and then this is basic setup. Okay, so if you look down here on the bottom right, what I have is, so I haven't executed this code yet, so this is kind of the baseline stats for the Jetson. So I'm executing a open source library. I will reference all of these open source libraries at the end to give credit. But this is called Jetson stats. You execute it by running JTOP, and it tells you how much CPU you're using for each of these, the amount of memory currently being used, the swap space, how much of your hard drive you're using, and then GPU utilization, and then disk space down here. So this is a great tool for benchmarking. We can look at CPU usage, memory usage, and we can even go and look at our, what version of everything is running. Okay, so we'll go back here to all, and now I will execute the code. And again, this takes a second to boot up to turn on the radio because it's doing those calibrations, and then it's just going to be reading continuously. Okay, so I think that we have started reading We have started reading now because you can see that the utilization of the CPU has kicked up a little bit, and so now we're operating. Okay, so this is kind of the basic baseline for reading full data rate to the Jetson on the AirT. Okay, so I will Control-C out of that, and now we are back to baseline, running at between 25 and 35% utilization there. All right, so now let's go back to our presentation. And that's what I have for you on the basic operation of the AirT. Now let's go into some actual applications. So this is where it's going to get good. So the first application that we will talk about is GNU Radio. Going back to our diagram, I will be running through this all session and highlighting the ones that I'm currently talking about. So now we will be talking about GNU Radio. So if you're not familiar with GNU Radio, it is an open source software-defined radio toolkit. Basically, it's a Python interface to C++ accelerated code. It allows you to easily create digital signal processing algorithms, but it does primarily use the GPU. So on the AirT, it will be leveraging the ARM processors. Now, there has been recent development by the GNU Radio team for RF NOC, that's RF network on a chip. So that allows for accelerated of FPGA programming, and we are working to try and potentially do some GPU support for both digital signal processing and machine learning. So GNU Radio has a GUI interface and a Python API, which is a GNU Radio Companion. So that essentially allows you to drag and drop these boxes. And those boxes all get turned into Python code that the user can use. So here's the demo that I'll be showing you. This is going to be a polyphase rational resampler. So you'll notice that our radio source, we are actually just going to use the UHD source. So if you have code that already leverages UHD, you can literally just point it to run the exact same code on the AirT. So this is the source that we use. So we set the sample rate to 125, tune it to 1.35 gigahertz. And then we send it to our polyphase resampler. So we are going to upsample by 16, and then we are going to down decimate by 25. And then the last thing that happens is we are going to send in the result to a frequency sync block. So that's essentially just going to plot the spectrogram there. And I'm switching over the connector right now. so that I could have my signal generator going in instead of the antenna. And let's switch over to our demo. Oh, and then this is kind of the program or the settings interface for the rational resampler. Okay, so now we're going to go back here. I'm going to go to full screen, and I have a different desktop for the GNU Radio block. Okay, so I still have my JTOP going over here, but what I am going to show you here in a second is that we are not able to keep up full rate on the by doing the processing on the ARM. So I'll hit play here, and that essentially creates Python code. So if we go to this, what it did was it created, so it's running now. What it did was it actually created this GNU Radio resampler.py. So if I open this, you can see what it has done is essentially turned all of these blocks into this Python code. So this is a great way to get started, is to just throw a bunch of things together in GNU Radio Companion, look at the Python code, and then just run with that. Okay, so, but what I am going to show you now is that, let's see here. That we are actually dropping data here. So and so you can see here, what I'm doing is looking at dmessage so I can see when there's a buffer overflow on the AirT, and they're happening pretty regularly, and that's to be expected. So we are running at 125 megasamples per second, capping out these ARM processors. These are embedded processors. They're not meant to handle this type of data. But you can see if we then take the data rate down, let's go to say decimate by 4, and I'll hit enter a few times. The amount of data getting dropped is significantly less, but we are still dropping data there. But when we go down to, say, 15 or even lower, down to 7, we'll start to hit a point where we are able to actually process real time. So that's going to be a limitation of the ARM and doing this type of processing in GNU Radio, unless you can GPU accelerate that. But you can see it did do a resample here. So we're no longer at 125 megasamples per second. We're now at 80 megasamples per second. And I'm sending in a tone. Look at my screen here. I'm sending in a tone at 1.3531 gigahertz, and that's exactly where it is. Okay, so I'm going to kill that. We can Control-C out of that, clear it, and so now we're back to baseline with the with JTOP. Okay, so now let's get out of our no machine instance and back to the presentation. So the next thing we're going to talk about is cuSignal. All right, so cuSignal is right here, and so we'll be comparing SciPy.signal to cuSignal. All right, so let's go briefly. I have borrowed some slides from Adam Thompson, who is on the NVIDIA Rapids team, who is the creator of cuSignal. cuSignal is an open source GPU accelerated version of SciPy.signal. So basically anything that's in SciPy.signal is now GPU accelerated in cuSignal. And there's certain things there where they had to write custom CUDA code in order to make it run fast, and we've been helping the cuSignal and Rapids team to get that stuff not only to be GPU accelerated, but to do things like leverage the shared memory architecture and also be able to get everything to run in real time. Okay, so if you're not familiar with Rapids, Rapids is essentially the NVIDIA push to GPU accelerate all of data science. So basically everything, all of these different toolboxes come together with Rapids, and Rapids then has Python bindings that are GPU accelerating all of this. So one of the nicest things is cuDF, which is similar to Pandas. But in this talk, we'll really be going through NumPy and CUPY and leveraging those. In a future talk, we will go with PyTorch and talk to you about that. Okay, so CUPY, I mentioned before, is a great library because it has the same function calls as NumPy, except for all of the toolboxes are GPU accelerated. And this is one of the pillars that cuSignal is built on top of. So let's look at the difference between NumPy and CUPY here. So essentially, everywhere that you have a NumPy in the code on the left for a Hilbert transformer, you can just substitute CUPY, and the code produces the same answer, and this one's GPU accelerated and this one's not. That is a tremendous difference from when I first started working with GPUs. Being able to have Python code that GPU accelerates is very, very significant. So now let's look at the same polyphase filter that we just showed in GNU Radio, but here we're showing it on the left in scipy.signal, and on the right I'm showing it in cuSignal. So recall cuSignal is GPU accelerated scipy.signal. And then I've got a diff screen going. This is the output of PyCharm, a very, very nice diff screen. So basically all we did was we changed. So first of all, let's walk through the scipy.signal. So the first thing we do is we import our packages, and then we define our RF parameters just like we did in the previous toolbox. Then we're going to create a filter. So here we're going to do a fur filter design. And then we are going to create our buffers, but we also need to create a different buffer for the output of the resample polyphase filter. So we feed that the buffer. This basically, you have to run this one time before your for loop down there to initialize the memory and get everything pinned. And then we pass it the window that we created up here. The next phase is to initialize the radio, just like we did on the past code, and then we run our tests. So instead of putting it in an infinite loop, I'm putting it in a finite number, I'm putting it in a for loop with a finite number of reads so that I can benchmark it. So we read the data off, that puts the data into the buffer. If the return code is -4, that means we drop data, and I'm going to increment the drop counter. And then I am going to resample. So that's going to take us from 125 megasamples per second to 80 megasamples per second. And then once I've done in reads, which is for 20 seconds, I am going to deactivate the streams. Then I'm going to calculate my throughput in gigabits per second. And I'm going to report how many times I dropped data. And I'm going to report how long the test was. And then I'm going to plot. So I put a custom, this is just a custom polyphase plot here. It is also part of the source code. So you can see the only differences here is instead of calling NumPy, I call CUPY. Instead of calling scipy.signal, I call cuSignal. There is a major difference here is that this can't support the same data rate as this, and I will demo that in a second. So this is a higher data rate. There is another thing here where you have to create a CUPY array of the window. See, the window comes out as a NumPy array, and we need to, and it also comes out as float 64, and we want to turn into float 32 because otherwise all of the computations will be governed by that float 64. So we're going to do a CUPY as array there. Then the buffer, instead of just doing a NumPy empty, we are going to do a signal get shared memory. So we're just defining our buffer to be shared memory there. And then we're going to resample. This use NumPy equals false is actually not necessary anymore. That is now the default as of a few days ago in the source code. Nothing changed here all the way down to the plot. The only difference there is the title of the plot. Okay, so let's go to this demonstration. So the Deepwave team and the Rapids team have been working very hard to bring this. So I am going to go back to the top right one. And let's look at Polyphase CPU. So this is the same code here. The only difference is that this is done in a Conda environment. So if you're not familiar with Conda, it's essentially a virtual interface for Python. So virtual environment for Python. Okay, so I'm going to do conda activate cuSignal. All right, so now we have our cuSignal environment activated. Instructions for doing this are in the Deepwave digital documentation. And now I'm just going to run Python Polyphase CPU. We're going to run that. We're going to look down here. Okay, so radio's on. Okay, so now we have cranked this up. This is about where we're functioning. No GPU really. This is just not doing much here. I will comment that we have turned off CPU 2 and 3. We run it in a custom power mode, which is max core in that comes on your ART. So this runs for 20 seconds and then reports out. So it should be getting close to done, and you see, so we did in fact drop data 2 times in 20 seconds. So that ran at 9.33, and I'm also realizing that I did not hook up the signal generator to this channel. So what we will do is we're going to run this test again. I'm going to decimate by 8 this time. And give me a second. I'm going to switch over the signal generator to the other channel. Looks like I have channel 1 on the code. Okay, so I will save this and we will run it again. And we shouldn't see any drop data this time because I have reduced the data rate enough to where scipy.signal can keep up. So again, I touched on this a second ago, but we have our own power profile that comes on the ART. So the 4 that are typically, or the 5 that are typically supported by NVIDIA are here. We added another one which essentially turns off the Denver, as you can see there, because we've been running into issues with that. Okay, so you can see the code here. So when we resample, that's what it looks like. So you actually can't see this because we had to resample so low that it is now out of band. So this is what your polyphase resampler looks like. All right, so that'd be a 3.353, which would be over here, unfortunately. Okay, so, but you do see that we dropped data 0 times in 20 seconds, and I would report this is the real-time throughput for the embedded CPU. Now let's switch over to the GPU code, and that's right here. And I'm going to run this at 62.5 megasamples per second. So we'll go Python, I can type. Okay, so I'll let that run, and we'll notice down here as this is running, the GPU will actually kick up quite a bit. I think we run at like 50, 60% on that. Okay, there we go. So you can see we're running somewhere between 30, 39%. We can go over and actually look at the GPU utilization over time. We are by no means capping this out. There is still room for other processing on there as well. Say, for instance, if you wanted to do inference on your new resampled signal, we did in fact drop data 0 times over that 20 seconds. This does actually not drop data at all. And it's running at 3.7 gigabits per second compared to the SciPy implementation on the CPU, which was 467 megabits per second. Sorry if I said bytes, I meant bits. This is 3.7 gigabits per second. And you can in fact see the result here, where we have the resampled data down here in the original signal right there. Okay. So that is the demo of the cuSignal aspect of this. And the last thing that I'm going to go through Get back to our presentation. All right, let's now look at the deep learning workflow. So I'm going to touch on this. We will have a deep dive into deep learning on our next webinar. Okay, so the first aspect that we're going to talk about is CBR. So this is a recent project that Deepwave Digital worked on with one of our partners into Citizens Broadband Radio Service. So essentially what CBRS is it's reallocating the Navy radar band when they're not using it. So you have to have sensors out here, they're called ESCs, that are detecting and discerning if a Navy is emitting its radar signal. Then those report their findings if they are seeing a Navy radar to a SAS, or if they are not, they report that too. And then that SAS can then sell commercial LTE services. These are things like private LTE and things like that. So what Deepwave Digital has done is we have said that this Navy radar, well, we're not really allowed to know the Navy radar waveforms because they're sensitive. So what we have done is we have created a humongous data set, something like 10 million different segments, and trained a neural network to detect and discern the presence of those signals. So the first step is to monitor the spectrum, then identify the emissions, report the presence of the priority user, and then distribute commercial services. So the first thing, let's kind of walk through. So that's an example application. I'm going to kind of walk you through how you would attempt something like this. So the first thing you have to do, so up here at the top we have collect data, train neural network, optimize, and deploy. Well, collecting data is a big one, and the AirT actually runs Ubuntu, as you've been seeing, so that makes it really nice for recording and labeling training data. And this is a typical setup that Deepwave would use, where we would use the AirT as kind of the command and control for this setup. So the AirT would maybe control a signal generator. The AirT itself could generate the signals. If you wanted something more controlled and extremely precise, you could get something like this MXG here. And so over Ethernet, we can communicate with this. You could also do USB or GPIO to other systems. So because the AirT it sends us a message to the MXG to say, hey, emit a particular waveform, I know what's coming out of there. It knows what's coming out of there. So we can say, hey, emit a waveform. It then emits the waveform, and we either cable connect it or antenna or transmit it over the air, and then we receive the data here in RH2. And because I was able to control all of that exchange, then I can now actually label this data. I can control the amplitude, I can control the noise level, I can control the power level, I can control the phase, I can control everything. So this, and because I'm controlling that, I know what the signal is, and that allows me to essentially automate the collection of training data, which is crucial for something like this. And then looking over here at the left-hand side, so what we'll do is we'll then run this through, say, a channelizer. Here I'm showing the different bands in CBRS, and we'll detect it, and we'll classify that and send that to a neural network. Okay, so the next aspect is training. So I've mentioned this already, so we support multiple training environments. Here I am showing TensorBoard. So TensorBoard is part of TensorFlow, and what we have done here is we kind of took the shotgun approach and trained, it looks like something about 204 different models to see which one was able to classify the radar signals best. We then take that best in breed, but you got to keep in mind that the best in breed there is not the one that classified it with the highest PCC. It's the one that classified it with the highest probability of correct classification, and also is the most computationally efficient. So it's that optimization problem. And we have another slide deck from NVIDIA's GTC conference in 2018, where we went into a deep dive of how to do that. So look for that on our blog page posts if you are interested. All right, so we then take what the neural network that we decide is our best in breed. We then run it through TensorRT for optimization. This removes unnecessary computations to improve efficiency, We also provide source code examples of how to do this. So if you're not sure how to do it, we provide that. We also have an AirPack software package that I will talk to you about in a little bit that walks you through step by step how to do this. Okay, so here's an example of how maybe what a convolutional neural network classifier would look like. So you've got your RF data stream in to a convolution, max pooling, flatten, all this stuff. There's likely multiple convolutional layers and multiple classification layers here. In the end, this is what resulted. So we have a white paper that you can download from our website on how to do this. So an RF signal comes in, or how we did this, an RF signal comes in to our receiver. We then run a channelizer, a detector, and then a DNN classifier. That's the neural network. So we're running all of this signal processing on, we actually used CUDA because this was before cuSignal was in its current state. We used CUDA to create the channelizer, to run the detector, and do the classification. There's also a client running on the TX2 and sending that out to the SAS network. The really impressive thing about this was that the team at Deepwave was able to get the GPU utilization to about 85%, and we're doing the channelization, the detection, and the inference all on the embedded TX2 GPU. CPU utilization is about 40% of one-arm core for processing and 30% of one-arm core for network I/O. And when we took this and got it got it tested, and it was able to achieve 99% detection rate and 95% classification accuracy. And to our knowledge, this will be the first known deep neural network in the telecommunications industry for signal processing. So we're really looking forward to getting this out there. And we use the AirT for all of it. So the AirT is the receiver and inference engine for this. So this is a great example of a enterprise level application that you can run on the AirT. But it's not just for CBRS. This is a signal classifier. So we believe that we can apply this to many other signal types. And please contact us if you are interested in looking at how this could be applied to your particular problem and if you want to work with us. Okay, so that's pretty much it that I have for today. I'm going to go ahead and give you a teaser for our next webinar. So today we covered mostly signal processing on the AirT and GPUs. We touched a little bit on deep learning, but that will really be a deep dive in our next webinar. That will hopefully be in the next couple of weeks, and I will be announcing the date very soon. And there we're going to go into a deep dive into deep learning, talk about inference, and then we'll go over AirPack. So AirPack is a source code software toolkit that our customers use to learn how to create a signal classifier for RF signals. So essentially, we provide synthetic data, labeled synthetic data. We provide a Python TensorFlow source code for a neural network. We provide source code to train the neural network, and we provide source code to deploy it on the AirT. So all of that is included in AirPack, and we'll go into a deep dive in that and more on the next webinar. Okay, so just kind of wrapping up what we do. So AirT is our main product line. We have two models of that. And AirStack is the software development environment. We went over that in detail today, so I don't feel the need to do that again. AirPack, we'll talk more about that next time. But that is our solution for teaching you how to train neural networks on signal data. Feel free to contact us. All of that information is in the bottom right. If you want, you can email us, or you can go and fill out our form online. Finally, I just want to give credit. I may have missed some of an open source library. I apologize if I did. It was not intentional. But here are all the open source tools that we leverage to make this webinar. And with that, I will take any questions.